In today's presentation, we will discuss properties of Fourier transform. From where we stopped in the last class, a few Fourier transform properties are discussed. Starting from 1 to 6 properties we discussed, like frequency, time shifting, frequency, linearity, and also time differentiation property. All these variety of properties we discussed, but still few more properties are there to see. And in today's presentation, what we are going to see about the remaining properties of Fourier transform, and also one problem I'll just take to understand how we can be able to find the Fourier transform. So from the last class where we stopped, from that we continue taking up the next property, that is convolution used property under Fourier transform. So the statement is given here. The first part is a statement out here under a convolution property. It says if x of t, if I do Fourier transform, I will get Fourier transform as x of j omega. If I have another kind of continuous time signal y of t, if I do Fourier transform for x y of t, I'll get the Fourier transform of that as y of j omega. There are two signals basically. It's Fourier transform, and the prove what I need to understand the convolution of these two given continuous time signal. That means I will take x of t convolution with y of t, that I will call it as z of t. If I do the Fourier transform for the convolution of x of t and y of t, I should be able to produce the output in terms of the Fourier transform, where it says combination of z of t. If I do Fourier transform, I should get z of j omega, but in terms of convolution, it is a product of the Fourier transform of x of j omega and y of j omega. So this is what we have to prove from left hand to right hand side. So we'll go with the proof for convolution property for Fourier transform. So if I say the known parameter, that is as per the definition of Fourier transform, it says for any continuous time signal, let me consider continuous time signal x of t, its Fourier transform x of j omega can be defined as integration minus infinity to infinity x of t into e to the power minus j omega t dt. This is what definition of Fourier transform for a given continuous time signal x of t. If it is given signal y of t, then I'll get Fourier transform as y of j omega, which is nothing but integration minus infinity to infinity y of t into e to the power minus j omega t dt. So this is the two Fourier transform of a given signal x of t and y of t. So if I take z of j omega, the Fourier transform of z of t, if I take, so integration minus infinity to infinity z of t into e to the power minus j omega t dt. But we said z of t is nothing but x of t convolution with y of t. I will replace for z of t. So it means x of t convolution with y of t. We replaced by z of t. So we got it x of t convolution with y of t. So we know this convolution from the convolution uh, conditions. We can understand this should belongs continuous signals convolution, nothing but it follows continuous integral. It is in the form of convolution integral form. So it takes the definition from the convolution integral between the two signals x of t and y of t. It says integration minus infinity to infinity x of tau into y of t minus tau d tau. This is what definition of a convolution integral, which is written for x of t convolution with y of t, and rest remaining are as it is written. So integration minus infinity to infinity over here e to the power minus j omega t dt as it is written. So next what we are trying to do, we just alternating the order of integration. I'll just take this integration along with x of tau outside. This integration I'll take it inside along with these two terms. So we are changing the order of the integrations so that we can get the inside whatever we written earlier. the integration minus infinity to infinity x of tau, which is written outside, and the other integration of whatever there on the outside, which came into the inside, integration minus infinity to infinity y of t minus tau into e to the power minus j omega t. So this is the parameter with respect to t, hence it is dt is taken along with this. D tau is outside because this d tau belongs to with the x of tau, so d tau is written in the outside. But for inside, whatever we written in the square bracket here, so for this we have t minus tau we are observing with respect to y of t. That's why. So I'll just make it as a single term. So we are going to substitute t minus tau is equal to some other parameter a. So if you do the differentiation with respect to the right and left side, so dt which is equal to dA. So differentiating with respect to the tau term, if I do it, so we'll get it in terms, sorry, differentiating with respect to left hand side t and right hand side a. So dt which is equal to dA, which we are going to write, because I just focusing on to the t term, because here the major factor of integration t is equal to minus infinity to infinity. So this belongs to integration with respect to t. So t have to be differentiated over here. Here it should be in terms of a. So dt and dA relation is required for us. So dt is replacing by dA, that is what one point, and t minus tau we are replacing as a. And if you take the exponential term, there we have t, so t need to be replaced by a plus tau. So this is what the change from this to this point after replacing t minus tau is equal to a. So what will happen for z of j omega is nothing but as outside the term as it is, integration minus infinity to infinity x of tau, but inside the bracket whatever written earlier, where integration minus infinity to infinity y of a into e to the power minus j omega, instead of t we have a plus tau dA instead of dt, d tau as it is. Now if you look, let me rearrange this particular parameter. You can take exponential, expand it, e to the power minus j omega a one term into e to the power minus j omega tau is another term. Tau can sync with x of exponential e to the power j omega tau can sync with x of tau. So integration minus infinity to infinity x of tau into e to the power minus j omega tau. This d tau you can take it here. This is one point or one set of term, and the other set of term integration minus infinity to infinity y of a e to the power minus j omega a into dA. So this is all with respect to a term, this is all with respect to tau term, but this looks very similar what we take on x of j omega. This is the integration, sorry, this is a Fourier transform of x of tau, this is the Fourier transform of y of a. So both are giving something the Fourier transform term. So I'll just represent this as x of j omega, this I'll represent it as y of j omega, where in between we have multiplication. So what we got initially, the convolution of z of t, x of t convolution with y of t, if you do the Fourier transform for that, the answer z of j omega will be the product of x of j omega into y of j omega. That is what the point we written here. Convolution in time domain, which is equivalent to in frequency domain, it is a multiplication of two terms. So this is the usually frequency domain notation. Whatever we say, the Fourier transform what we obtain, that is in the frequency domain. Okay, so this is the convolution property for Fourier transform. So moving on to the next is integration property for Fourier transform, and its a statement goes like this: if x of t, if I do the Fourier transform, so I'll get x of j omega. Okay, forgot to write x of j omega here, so you can make it x of j omega. Then integration minus infinity to t of x of tau d tau, if I do the Fourier transform for this, I'll get 1 by j omega x of j omega. So integration of your given input x of t, if I do, and if I do Fourier transform for that, it is 1 by j omega, something a parameter which is taken out from x of j omega frequency domain. So this we can take it and we can solve it by taking only towers to the x of t term. So how we can take x of t term? By taking up the expression of x of t, we are going to write it as d by dt of integration minus infinity to t x of tau d tau. So if you look this, we have differentiation, we have integration. It can opposite to each other, we can take it out together. So what is remaining is x of t. That is what the expression or expressing x of t in terms of differentiation integration together. So if you look this, so what we are going to do, let me take the Fourier transform for both sides. Taking a Fourier transform for right hand and left hand side both. So Fourier transform of x of t, Fourier transform of d by dt of integration minus infinity to t d x of tau d tau. So Fourier transform of x of t, we written here x of j omega, that is directly x of j omega. So Fourier transform of differentiation. So this property we saw earlier as in terms of the previous class, where we studied about the Fourier transform of differentiation will give, if I want to say it, Fourier transform of uh, d by dt of x of t, that is nothing but it is j omega into x of j omega term, nothing but j omega with the Fourier transform of this x of t term. D by dt of x of t, I have to consider this. So d by dt means j omega, then this term will be x of j omega. So this I have to Fourier transform again. So j omega Fourier transform of x of t term, nothing but here it is integration minus infinity to t x of tau d tau. So this is what we obtain from differentiation property for the right hand side. Further simplification we can do it, but I'll just take j omega to the other side. So what is going to be happen, 1 by j omega into x of j omega, which is equal to the Fourier transform of integration minus infinity to t x of tau d tau will be 1 by j omega x of j omega. So we received the answer, the integration of x of t. If I do the Fourier transform of that, so I'll get 1 by j omega x of j omega, hence the proof for integration property. So this is how we can finish the integration condition for the Fourier transform signal. So next property is the modulation. Um, Modulation property is defined like this. If x of t, I have two signals, continuous time signal x of t and y of t. If I do the Fourier transform of x of t, I'll get x of j omega. If I do Fourier transform of y of t, I'll get y of j omega. Then the modulation, in the sense the multiplication of x of t, if I do the Fourier transform of that, what I should get. So z of t nothing but the product of x of t and y of t. So if I do the Fourier transform of this, I should get z of j omega, but this term, as I have to write, it is 1 by 2 pi of x of j omega convoluted with y of j omega. So the product of any continuous time signal and its Fourier transform will give the convolution sum. Convolution with respect to, with the convolution with respect to the frequency domain. So let me prove this. If I want to prove this, I just need to have x of j omega and y of j omega. So what we can take it from the Fourier transform definition, we can go with x of, for x of t signal. If I do the Fourier transform, I should get x of j omega, which is equal to integration minus infinity to infinity x of t into e to the power minus j omega t dt. For y of j omega to get, I should have integration minus infinity to infinity y of t e to the power minus j omega t dt. Suppose I have z of j omega, to get I should take integration of minus infinity to infinity z of t e to the power minus j omega t. This is all from the definition of the Fourier transform. But we know z of t means I should need to take as x of t into y of t. So we are replacing z of t as x of t into y of t. So what we are going to have, we know from the definition of inverse Fourier transform how to get x of t from x of j omega. So we can get it from x of t, which is equal to 1 by 2 pi integration minus infinity to infinity x of, instead of j omega, I already considered j omega here, and so that's why I'll just take instead of omega, I'll take beta. So x of j beta into e to the power j beta t d beta. So d omega, instead of omega, we have taken beta here, that is the different factor to be represented already, because omega is considered earlier. So I'll just take an beta over here. So this is what the inverse Fourier transform, what we can call. From the Fourier transform, I'm just getting back the inverse condition, that is getting back the x of t. So we know x of t. So what we can do, this x of t, whatever we have x of t value, we can substitute in this equation. So what is going to be happen, integration already there, along with for x of t it is 1 by 2 pi integration minus infinity to infinity x of j beta e to the power minus j e to the power j beta d beta with y of t e to the power minus j omega t dt. So this is what we are trying to do. So if I substitute that, we are going to have that same equation in this format I just mentioned earlier. So what we need to do now, we have two integration. Let me changing the order of integration. So if you change this factor inside the square bracket, what we have x of t value, that is integration factor is defined with respect to beta. So x of j beta goes along with this integration outside. So nothing but I'll also take 1 by 2 pi, 1 by 2 pi outside, integration minus infinity to infinity x of j beta, that is outside, however I considered. So within the inside set, I will take this integration minus infinity to infinity with y of t e to the power j beta t along with e to the power minus j omega t. What is going to be happen? Club together. So e to the power minus j omega within the bracket omega minus beta into t dt and also d beta can be written here. So now if you look this part, the second part of the integration, so integration minus infinity y of t into e to the power minus j omega minus beta t. So this looks a factor. Suppose instead of this e to the power minus j something like omega t with dt if you consider. So this together it is can produce something like y of j omega. So instead of this is one single term, let me consider omega beta as one single term, something like z. So integration minus infinity to infinity y of t into e to the power minus j z t dt. So if you do this, this is the definition of inverse for Fourier transform. So from the Fourier transform, sorry, not this is this should be an from the Fourier transform, not inverse. From the Fourier transform, what we can have this equation as y of z z is nothing but omega minus beta. So y of j omega minus beta we will get. So d beta as it is remaining, x of j beta as it is remaining, integration as it is 1 by 2 pi. But what you can look now, with all these integration factor 1 by 2 pi, you can keep it as it is, integration minus infinity to infinity x of j beta into y of j omega minus beta d beta, that is nothing but x of tau into y of something like t minus tau into d tau. This looks in that format. So what do you mean by that? That is the definition of convolution integral. So what you can say, x of j omega convolution with y of j omega. So I'll just take whatever t term have to be taken. So t term is j omega. So x of j omega convolution is y of j omega outside 1 by 2 pi as it is. So hence we proved the multiplication in time domain will equivalent to the convolution in the frequency domain. So this is how the proof which we can get under the modulation or multiplication of continuous time signal, where it can represented in terms of convolution in the frequency domain. Next is Percival theorems. This is however we earlier also we saw same theorem under Fourier series also. This is quite different over here representation. So let me look this Percival theorem. First of all, the definition of Percival theorem, it says if x of t I do the Fourier transform, what I can get, x of j omega. Then if suppose I do the integration minus infinity to infinity x of t whole square dt, that is nothing but an energy equation for x of t. So energy with respect to x of t, if I want to calculate, I should take this equation, integration minus infinity to infinity x of t with magnitude whole square dt. So this equation will say as energy equation, but in the sense it will be under Fourier transform. If I do the Fourier transform, uh, we will get it in terms of 1 by 2 pi integration minus infinity to infinity x of j omega whole square d omega. So this is also in the frequency domain also will be in energy form itself, and we will call this portion x of j omega whole square is known as energy density spectrum of the signal x of t, where this initial function will call it as energy of x of t signal. So energy of any continuous time signal will lead to the energy density spectrum of that particular signal. So this is what Percival theorem which we need to prove it. So I start with the left hand side of the whatever I want to prove it. I'll take the left hand side, that is an energy equation over I said. So I'll take that energy equation equal to integration minus infinity to infinity x of t whole square dt. I'll take that as it is directly. Let me split this x of t into two parts, because the magnitude, if I remove it and if I separate it x of t whole square, this is one part is negative, one part is a positive term. That is, however, if I take the magnitude terms, if I remove it, the two values are coming into picture, plus or minus. So plus value I'll say as x of t, and the negative value I'll take it in terms of imaginary, so x star of t dt. So there is a star is in the sense I just take it in terms of imaginary function. So let me substitute x star of t in terms of the definition of inverse Fourier transform. It says 1 by 2 pi integration minus infinity to infinity x star of j omega into e to the power minus j omega t d omega. That is what from the definition of inverse Fourier transform for x of t, but here I taken for x star of t. So x of t as it is, dt as it is, integration minus infinity to infinity as it is. So next what we need to have, we have two integration. Let me interchange these two integration. So what is going to be happen, 1 by 2 pi integration minus infinity to infinity x star of j omega. But within the bracket I take this integration along with this integration minus infinity to infinity x of t e to the power minus j omega t dt d omega outside. So what we going to happen, see, this term is integration minus infinity to infinity x of t into e to the power minus j omega t dt. This is the definition for Fourier transform. So I can write this term as x of j omega. So what we got now, 1 by 2 pi integration minus infinity to infinity x star of j omega into x of j omega d omega. So x star x. So this you can club together in terms of square with magnitude. So 1 by 2 pi integration minus infinity to infinity, with under the magnitude we can say x j omega whole square d omega. So what we got this as energy equation simplified in terms of the in terms of frequency, we started from the continuous nature, we got it in the frequency domain. So Fourier transform, which is represented from the given signal into the energy density spectrum. So this is how we can prove it, Percival theorem for Fourier transform. So the next one is duality property. This is the last property where I just wanted to list off for Fourier transform. Duality in the sense it is defining, we'll discuss here. The statement I'll just take first, x of t, if I do Fourier transform, I know this is x of j omega, but if I do the duality in the sense replacing t term by jt, so nothing but that is the imaginary term which is included with the t, that is what consisting either real and imaginary part for t. Then x of j omega t, if I consider, if I do the Fourier transform for this x of j omega t, I'll get 2 pi into x of minus omega. X of minus omega we will get. So let me try to prove this. So how to prove? So I just need to start from the x of t, that is what only the option left out, because I cannot take it x of j omega. So I just need to start with x of t, because t is related with jt, so we can take it as x of t itself. So x of t we know as from the inverse Fourier transform as x of t is equal to 1 by 2 pi integration minus infinity to infinity x of j omega into e to the power j omega t d omega. So over here for this, replace t by omega and omega by t. So interchange t and omega so that we can get, wherever t we have to write omega, wherever omega is there we have to write t. So x of omega is equal to 1 by 2 pi integration minus infinity to infinity x of j t into e to the power t omega. I can also write e to the power j omega t, no problem, dt. Instead of d omega we have to dt. So next we replace omega by minus omega. Omega by minus omega, we get x of minus omega 1 by 2 pi integration minus infinity to infinity x of jt as it is into e to the power minus j omega t dt. So what is going to be happen? I'll just take 2 pi to the other side. So 2 pi into x of minus omega, which is equal to integration minus infinity to infinity x of jt into e to the power minus j omega t dt. So if you compare the right hand side in the standard form, x of j omega is equal to integration minus infinity to infinity x of t into e to the power minus j omega t dt. So this is taking x of j omega. So this how I need to write this part as 2 pi x of minus j minus omega. So I just need to write x of jt because this is j omega t. Actually this is e to the power minus j t omega. So jt is need to be written. So x of jt. So x of jt, if I do Fourier transform, I can get it 2 pi x of minus omega. So this is how we can prove the duality condition under Fourier transform. So here we listed out all the Fourier transform properties, and almost of all the properties are very important as per the exam point of view. If you look for the model question paper, there are few questions. Any questions out of all these 11 properties, any questions can also be asked, but in exam model question paper, any two of the properties they asked, so any can be asked. So be prepared, look into these all these kind of properties, varieties, how it need to be solved, go through all the proofs, very important concept. So based on all these property, we are going to look into the some of the problems, and here also I have taken one set of problem to introduce the problem on Fourier transform. So let me look the problem statement first, and we'll try to solve it. This is quite easier compared to the a probleming under this particular section. So obtain the Fourier transform of a given signal x of t. X of t is like this, e to the power minus at into u of t, where a is greater than 0. So draw its magnitude and phase spectra. So given x of t, for this I have to find x of j omega. That is what Fourier transform, in the sense Fourier transform of x of t they have asked. So x of j omega I have to calculate first, then for that I have to find magnitude of x of j omega, and also the phase of x of j omega can need to be calculated. This is what from the problem statement. So solution. So as per understanding all this point what we need to calculate, so the solution need to be taken. First they said to find the Fourier transform. So I just have to calculate x of j omega for a given x of t. So x of j omega, we know that from the definition, x of j omega is equal to integration minus infinity to infinity x of t into e to the power minus j omega t dt. This is already we know. Let me substitute it for x of t. So what you mean by x of t? It says e to the power minus at into u of t, but u of t is always 1 when 0 to infinity have the value for t. So integration limits I can limit to 0 to infinity rather than minus infinity to infinity. I can take it 0 to infinity. For this, e to the power minus at, this u of t becomes 1 into e to the power j omega minus j omega t dt as it is. So I'll club these exponential terms together, e to the power minus j omega plus a into t dt under the integration 0 to infinity. So let me take the integration. What we will get, e to the power minus j omega plus a into t divided by minus j omega plus a. So integration limits from 0 to infinity, the limits which is 0 to infinity. First infinity you apply, you will get 0. Next minus of the terms, 0 is applied. 0 means the numerator becomes 1, so minus minus becomes plus. So 1 by a plus j omega is x of j omega, where a is greater than 0. So we got x of j omega as 1 by a plus j omega. Let me simplify this x of j omega in terms of to get the pure real values and imaginary values first, so that we can find the magnitude and phase spectra properly. So first I'll rewrite this x of j omega, answer 1 by a plus j omega. What we got, we multiply and divide by a minus j omega, so denominator becomes a square plus omega square term, but numerator I'll split it, a minus j omega, under denominator we have common a square plus omega square, so that a real term and imaginary term for x of j omega. So if I want to calculate the magnitude, then what I just need to take the square of real term plus square of imaginary term under root. So that is what the definition, how we need to calculate the magnitudes of real and imaginary term. So if you simplify this, I'll get as root of, under root we have 1 by a square plus omega square term. So this is what the magnitude equation what we got. From this, take some values for x of j omega, take some values for omega along with, sorry, this is omega here, we just missing here, this is omega. So omega versus x of j omega, where you take the graph as a value which changes at 0. If you consider, we can have the maximum value as 1 by a if omega is 0. So what is going to be happen, 1 by a we will get maximum. So when omega is equal to a, so what is going to be happen, this is a square plus a square, so 2a square, 1 by root of 2a square means 1 by root to 2a, so that is what we can get it under this, and 1 by root 2 into a, the, and I think I need to be rearranged here, so root 2 into a, separately you have to write it at a and minus a. So rest of the values are exponentially decreasing with respect to the vertical axis. So this is how the magnitude plot we can plot it. But for the phase value, if I want to calculate, it is tan inverse of real term, sorry, imaginary term divided by real term. So imaginary term is minus omega by a square plus omega square. Real term is a by a square plus omega square. Denominators are cancels. Remaining is tan inverse of minus omega by a, minus you can take it outside under tan. So minus tan inverse of omega by a. Substitute omega values, so as along with the omega with the different values, so we'll get the like hysteresis graph of equation, so you can get it. So this is varies in terms of different angles. So maximum angle what we can get till reaches as a pi by 2, that is the possibility with the maximum value. So for the phase, so this is how we can plot the graph for a phase graph for the given signal x of t in terms of x of j omega. So this is how very simply we can calculate it, the Fourier transform of a given signal x of t, which is equal to e to the power minus at into ut, where a is greater than 0. So thank you for listening. So all the properties you just try to remember it before attending to the next session, and based on all the variety of problems, properties, statements, they are trying to solve some other few problems. Thank you.